Hi, welcome to Calculus 3 lecture series. And we are in the unit about the vector and geometry of space. And we are in the lecture number 5. And the topic we'll talk about here is the equations of line and the planes in the R3 space. So this is our second video on the lecture number 5. So the first video we did, the first part is how to write the equations of lines in R3. So the second video, we're going to do the second part is how we're going to write the equation of planes, in the R3s here. Okay, so before we go to our problems here, let's take a look. Okay, so let's take a look and get a little bit like a brief lessons. What is the plane? How do we find the planes here? Okay, so let's take a look here. So if here, okay, so this is my coordinates planes here. So this is XYZ R3, and now I have a planes here, right? So I have this plane here. So let's assume this plane is in the R3, all right? Okay, so now how do I uniquely determine these planes here? So a plane R3 can be uniquely defined by, we call this the normal vector. What is the normal vectors here? That means if you have a vector which is perpendicular, okay, so if you have a vector which is perpendicular, so like a perpendicular to this plane here, all right? So now this vector will be uniquely defined this plane. So like if this is a vector, I call that this is a vector is A, B, and C here, all right? And then, if this plane also passing through a point, let's say that this is x0, y0, z0 point. And this point here, let me write this here. So in here, let's put this one, maybe it's better here, all right? So this is my x-axis here, all right? So then I have a point here. So let's write down the points first. So mark the points here. Okay, so this is the point, and this is the point, and then we can put it into a vectors here. This is the pointer x0, y0, z0, right? But then if you can also put it into we can say this is the vector r0 generated by this point here. All right. So now this is a vector. You can put this is a vector. It's gonna go right here. So now in here, in the planes here, right? You can. So now we can have any other points here. Right, so if any other points, I call that this is x, y, z. It's just like when we in R2, right? So we say any other x point in the line. So that means any other point in x, y, z. Then how do I write this, how do I write this planes here? So if you take a look here, right? So this is the point. So this is the, okay, so this is the vector, go like this, right? So this is the vector, so kind of located in the R3s here. So what is this, this one's here, this vector laying on these planes here, right? So this point is here, this point here. So this vector laying these planes, laying on top of this plane here. So this vector, if you use the, like the vector notation we learned like in the, like in the second, in the second lecture notes, this one's here, this is R0, right? And this is any R here, any XY, you can put as vector R. So what is this red ones here? this red one is the vector r minus r0, okay? Since the ABC, right? So this one, since this normal vector uniquely defined, these planes here. So because this is the, because this is a orthogonal vector, right? It's perpendicular. So I know we can put this is like, we call this the n vector. So I know from the dot product, so I know the n dot, what? N dot, this red one, r minus r0. This is the vector laying on the top of the planes, right? So this, what we're going to give you, will give you zeros here, right? Because it's perpendicular, so we use the dot product of cosine theta because it's 90 degrees, so cosine 90 equal to 0. So that means n dot r, right? So minus n dot r 0 equal to 0. So I know the n dot r is going to equal to the n dot r zeros here. So this is the vector form of a plane here. So if you kind of write it out, right? So then here this is n dot r minus r0. So what is r minus r0? This is the vector x minus x0, y minus y0, and z minus what? Z0s here, right? So that means n is a, b, c, and the dot here, x minus x0, y minus y0, z minus z0 equal to 0. So that means you can write this is a, x minus x0, plus b, y minus y0, plus c, z minus z0s here, and equal to zeros here, right? So this is the form we call, this is the scalar form for the plane, how to write a plane, see here. So did you see here? So this is very similar like in the R2, right? So this is the kind of the similar. So see here, this is the A, B, C. So those are the constant, right? So those are the constant for my plane. And what is those constants form? Is form like a normal vectors here, right? Okay, so that's what, that is what we call is the plane in the R3 here. So now let's take a look here. So this is what we say here. So let's see here, we talk about what is the normal vectors, right? So it's the vector perpendicular to this plane here, right? So we said now in here, just like we explained here, so you can have a vector form, you have kind of a scalar forms here. So remember, in order to get a plane here, so this is the key, right? So this is the key constants. Those are the constants from the what? From the normal what? From the normal vectors here, right? Okay, so let's, okay, so then the next things here, let's take a look. Okay, so the series here, we say if n and b are non-zero vector, if both these vector in the plane, then of course we know that, right? So we said a cross b, that's why you generate a vector perpendicular to both a and b, right? So now we say, okay, so this is the normal vector, right? So for every linear equation, ax plus by equal to c is the equation of the plane in 3-dimensional space. And the key things here is, right? So with the normal vector ABCs here. Then the theory number 2 is also a very important theory, it's a very beautiful theory. They said when the two planes, they are not parallel. If two planes, they are not parallel, then they are going to intersect in a line. So the angle between these two intersections are going to be is just the angle between the two normal vectors. So if you kind of kind of in the real life, you do a demonstration, like you put like one plane with a normal vector and other plane with a normal vector. Then when you try to intersect those planes, then you will see the normal vector is kind of, so it will form the same angle like the plane forms here. All right, so now let's, okay, so let's take a look our next one's here. So let's see here. Let's go to the next page. Let's start to take a look at some practice problem. Okay, so here is our first very easy practice problem. So it says find the two forms. So we have a vector form and a scalar form. When the, this plane passing through this point, a point, and so the normal vector is kind of like a direction vector, right? So it's with normal vector, this 625. So we know, oh, that's pretty easy, right? So the vector form, okay, so vector form, like we say, what is the vector forms here is n dot r is equal to what? N dot r zeros, right? So the n dot r, so n is 625. So I have 625 dot r, right? So dot r is equal to the 625 dot 823, right? Dot 823. Okay, so now we have, this is just the 625 dot r is equal to 67, right? Okay, so if you do the dot products here, so it will be 67. Then what is the scalar forms here? So the scalar form is just like you use what? You use your normal vector as the constant, right? So it will be what is 6, then the x what? Minus 8, correct? And then plus 2, y minus 2 plus 3, y minus 5 equal to what? Equal to 0. All right. Okay, so it's a pretty straightforward, right? So that's so if you simplify a little bit, so this is 6 plus 2y plus 3y, 3z. Not careful here, right? So here, okay, so this is z. This is z. Okay, so the z minus 5 plus 3z is equal to what? Equal to 67. All right. Okay, so number 7 here, let's say find the scalar form of the equation of the plane passing through 3 points. From our earlier geometry class, we know the 3 points uniquely defined a plane. So every time we find a plane, so what is the key part we have to have? We have to have a normal vector, right? Because normal vector decide the constant of the plane. So in order to get a normal vector, how do we find it? So we need to use a cross product concept, because a cross product is find the vector perpendicular to both, right? So now I can create two vectors. I said the vector A is equal to PQ, right? Okay. So if the vector A is equal to PQ, so it's a Q minus 1, so it's a 2, negative 3, and 3, that's right? And then we're going to produce another one, we say it's a PR here, okay? So it's a PR. Then the PR will be 3, negative 4, and what? 2 minus 1 is 1, right? So it's 3, negative 4, and 1. Okay, as long as we do that, then we can find a normal vector. So what is a normal vector? Normal vector is A cross B, because both these two laying on the plane. So when you do the cross product, then you will produce a normal vector to both those vectors. And at the same time, this normal vector is perpendicular to the plane, see here, right? So now if you kind of remember, then you do this, right? IJK, then you put it 2, negative 3, 3, 3, negative 4, 1. I assume you know how to do that. And so here the answer is 9i. I already did that, plus 7j, and plus k here, right? So now I know my normal vector is what? It's 9, 7, 1. Then you can use this normal vector and then find any points you want, right? So I can say, okay, I'm going to passing through these points here, right? So so you will do like this. So you use the normal vector. So it's 9, what? X minus 1 plus what here? 7, y minus 3, that's right? And then plus 1, z minus what? Z minus 1 equal to 0. Then you simplified it a little bit, so you will get a 9x plus 7y plus z equal to what? Equal to 31. So this is the scalar form of the planes here. All right, okay. Let's take a look at the next problem here. So the next problem, let's say find the equation of the plane goes through the point. Okay, so I have a point. Okay, so we need to have a point. Then we need to have a normal vector. And then they say it's parallel to this plane. If this is parallel, that means what? That means, you know, this is the normal vector for these planes, right? So it's a 2, 5, 2. So if two planes are parallel, so what happened to their normal vector? The normal vector will be what? Will be parallel also. So now I know this one's here. I can say that my normal vector will be the same as this plane. So it's a 2, 5, 2. It's good. Okay, so it's 2, 5, 2. Then it goes through this point. So then we do the same thing. So this one is pretty simple, right? So it's 2 the x minus 1 plus 5 the y minus 2 plus 2 what? The 2 z minus 3 equal to 0, right? Okay, so now you simplify it a little bit. So it's 2x plus 5y and plus 2z is equal to what? Is equal to 18, right? All right, so that's pretty good. Okay, let's take a look at numbers 9 here. So number 9, they say find the angle of intersection of these planes here. So, okay, so we just learned the intersection of the plane will be the same angle in their normal vectors, right? So those are their normal vectors. So I know the first normal vector is 3, 1, 3. This is for this planes, right? So the second normal vector for this plane is 6, -3, -2. So because the angle intersected by the plane is the same as the angle intersected by these two vectors, right? So we know the cosine theta is equal to what? Equal to the n1 dot n2, and then we have a length of the n1 times the length of the n2. So n1 dot n2 is 18 minus 3 minus 6. Okay, and so in here, this is 3, 9 plus 1 plus 9, so it's 19. And this one, 36 plus 9 plus 4 is 49. Oh, that's pretty good. So this is 49. Then this is 9. This is 19. 49 is what? Square roots. So this is 7, right? So 49, square root of 49 is 7. Okay, so now these numbers here approximate to the 0.29496. All right, so what is my angle theta here? Angle theta is just be the arc cosine 0.29496. So it is about 72.8 degrees. All right, okay. All right, so let's That's pretty easy, right? Okay, let's take a look at a few more of those planes problems here. As long as you capture the concept about normal vector, then I think a lot of those problems are very simple. So the first thing is here, they say, hey, the equation of two planes, this and this, show these planes, they intersect. All right, so let's see here. So the first things here, we still say, okay, for these planes here, right? So the normal vector for this plane is what? Is 2, 1, -1. The normal vector for this planes here is what? Is 3, 1, 2. So are they the multiplications for each other, the scalar multiplications? No, since n1 is not equal to a constant c times n2. So they are not the scalar multiplication. So that means n1 is not parallel to n2. If the normal vector is not parallel, that means the plane number 1 is not parallel to the plane number 2 here. All right, okay. So the parallel should go to the back. So this is not a good parallel sign. So it's that means it's not a parallel, right? Okay, so now the next one's here. We're going to learn a new thing. Is find the line of the intersections here, okay? And so we know, the line of the intersection for the planes, right? So forever this line, the line of the intersections here from the, if you try to do a demo by yourself, so this is going to be orthogonal to both N1 and N2. Okay, so it is very difficult to try to draw the picture and draw the picture like in the flat surface here. But if you do the real life demonstration, you put a plane and then put a normal vector, and another plane, another normal vector, and then you intersect these two planes, then you will find that the line it produces is perpendicular to the both normal vector. All right, so because the line it produces both to the normal vectors here, so that's why I'm going to find what is this line's directions looks like, right? So I do the cross product, right? So this is ijk. So the cross product is 2, 1, -1, 3, 1, 2. And I believe you can do it. So the answers for this one is +3, -7, -1. All right. Okay. So this is the direction vector. Remember, right? So direction vector for what? For the lines, right? So this is a direction vector for the lines here. So remember, if this is a direction vector for the line, in order to write a line, so what do we need to do? We need to what? We need to find a what? Find a point. All right? So we need to find a point. So how, that means for these two planes that intersect, we need to find a point. So let's say here, these two planes, this is 2x plus y minus z equal to -4. This is 3x plus y plus 2z equal to 5 here. Okay, so let's see here. We say, okay, I need to find the point. So let's say, let's see if I set x equal to 0. You can set y equal to 0, z equal to 0. Doesn't matter, right? So I think, let's see if we can find a unique solution for y and z. So y minus z equal to -4. Then this is the y plus 2z equal to 5, right? So you use the equation number 2 minus equation number 1. What do you have? You have 3z equal to 9. Okay, so that means z equal to what? Z equal to 3. So if you z equal to 3, you substitute to here. So y minus 3 equal to negative 4. So what is y? Y is negative 1, right? So we find the what? We find the point. What is this point? 0, negative 1, and 3, right? So I got my point. So this point is 0, negative 1, and 3. As we say, you can always choose different. You can choose the y equal to 0, and then solve for x and z here. Okay, so now I have a directional vector, and I have a point. So let's use the symmetric one. So my answer will be x minus 0. So it's x over 3 is equal to y. So it's y plus 7, negative 1, right? Oh, no, I've got a backward here. So the 7. Okay, so that's the point, right? So you're not careful. So this is y plus 1, and it's negative 7. And then z is z minus 3, and the negative 1s here. So this is what type of the form we talk about in the line. This is, we call it the symmetric forms here. Okay, all right. So now we find the, okay, so we want to find the distance, okay? So next one's here. So if I have a plan, here is x3, x plus 3y plus 4z is equal to 12. Then I have a point 1, 2, negative 2 here. Then what is the the distance? Do you remember, like when we did a cross product? So we derived the formulas here, right? So the distance here will be what? Will be the square roots of the normal vector square. So it's 1 square plus 3 square plus 4 square. Then the top will just be this one. So it's 1, put the absolute value, 1 times 1 plus 2 times 3 plus negative 2 times 4, right? And then you move this over, right? So it's minus 12. So this will be the distance. And we did this in the exercise from the cross product, all right? So now in here, you will find these answers here. This is 16, 25, 26, all right? Then the top here are going to be the negative 13. So of course I cannot have a negative distance. So it's 13 over square root of 26. Okay. And now, okay, so for the distance between, find the, so the next problem here is to find the distance between the two parallel planes here, right? So think about how can I find the distance of the two parallel planes here? So the distance of the two parallel plane, okay, and let me see another close. Okay, so let me see, we can get it smaller here. Okay. Okay, so the distance of the two parallel planes, that means first, if I find a point in the one plane, okay. Okay, so now, so in here we say, okay, so from the 11 we know, if you give me a point in the plane, then I can just plug in and get the answers, right? So here is the same, all right? So that means I need to find a point, pick a point in the plane. So let's say here, I will pick a point on the first plane here. What you mean, pick a point? That means I choose a number to, if that number satisfies this equation, then it will be the points on these planes, right? So I would say, hey, let me choose y equal to 0, z equal to 0. Then I have a 2x equal to 10, then the x equal to 5, right? So I know the point 5, 0, 0 going to be on this plane here, right? If this is on this plane, hey, now I know how to find, so if you have two planes, think about it here, right? If these two planes are parallel, so you choose a point here, then that's what means the point, the distance from this point to this plane will be the distance between these two planes here, right? Okay, so what is the distance here? Oh, we can just use the same formula like we had in the 11. So it's 2 to the square plus 3 to the square plus 7 to the square. Then you plug this point, right? So this will be 2 times 5, correct? Then plus 3 times 0, then plus 7 times 0, then minus 134. Okay, so now you get it here. This is the 2 square 4 plus 9 plus 49. This is 62. And this is negative 124. So it's 124 square roots of the 62 here. All right. All right. So these two, they are really related. So just like you can choose any of the points you want, right? So you can choose like y equal to 1, z equal to 1. So 3 plus 7 is 10. Then the x will be equal to what? It will be 0. So I know the 0, 1, 1, this point will be on this plane also. Then you can do the same thing. Plug in and get the same answer. Okay, that's pretty cool, right? Okay, so let's take a look at our last problems here. Let's say, hey, where is this line intersect the plane here? Okay, so the line intersect the plane. Okay, so now you take a look. You say, okay, so this one's here. This is a parametric form, right? So that means x minus 1 equal to t. Then this is y plus 2 equal to what? 3t. And z minus 1 equal to what? 2t. Did you see where I'm going? Then x equal to 1 plus t. Then y is equal to 3t minus 2. Then z is equal to 2t plus 1. Okay, so if this line intersect, right, the plane, that means that whenever I have x, y, z has to satisfy this plane equations, right? So x is what? 1 plus t minus 3. So this is 3t minus 2, right? And then plus z is 2t plus 1 equal to the negative 6. Okay, then I'm solving. So this is 2 plus 2t minus 9t plus 6 plus 2t plus 1 equal to negative 6. Right? So that's why you simplify, I get a negative 5t is equal to negative 15. So t is equal to what? T equal to 3. So when the t equal to 3, so x equal to what? 4, right? Then y is equal to 3 times 3, 9. 9 minus 2 is 7. Z is equal to 2 times 3 is 6, so it's 7. So we know where is they intersect? They intersect the point, at the point. What the point here? 477. All right, and that's it. Okay, so that is about the plane. How to find the plane in the R3. So what are some key concepts you guys can take away with this one? So the first thing is here, a plane is uniquely defined by the normal vectors, right? So the normal vector is the one perpendicular, right? So it's the one perpendicular to this plane here, right? So the normal vector A, B, C decide the coefficient of that plane. Then if you're passing through any given points here, then that's how do you write it, right? So you use the normal vector as the coefficient, right? So then this is the standard form of a plane. We call it the scalar form of the plane. So like, so that's the first things. Then like next things we say, if the plane, right? So in the parallel, that means the normal vector parallel, all right? And then the other ones here, we say it's very important. It's the angle, you know, when two planes intersect, this angle will be the same angle like two normal vector, in, you know, like the intersect, right? So that will be a very useful things. Then the other things here is we said, how do I find, you know, when the two planes they intersect, they will produce a line, right? So that line is going to be what? It's going to be perpendicular to both of the normal vectors, right? From the both planes here. Those are the few key concepts we need to remember. And that's it. And so we finished the sections, we finished the lecture number 5, how to find the equations of the lines and the planes in R3. Very interesting, right? It's quite different than what we learned, you know, when we were in the high school, the geometry classes, right? So especially the line is very, very different, right? All right, so that's it. And so I guess we're going to finish our last topic in our next video. And that will be the lecture number 6. So we're going to take a look at some figures and in the R3 space here. Okay, that's it. You guys have a good day and I'll talk to you later. All right, bye-bye.